This video describes a model of oil drilling in a given reserve over a 5-year period. The goals are to estimate capital expenditures each year and to estimate the number of wells in operation each year. These depend essentially on the amount of oil in the reserve relative to how much there could be, as explained in the following. The fixed inputs appear in rows 4 to 7. These are estimates made by experts of the minimum and maximum capital expenditures per year, as well as the minimum and maximum number of wells per year. The question is where the actual values will fall within these extremes. There are 3 sources of uncertainty, as indicated in rows 10 to 12. The acres of the oil reserve, the depth in feet, called the net pay, and the recovery rate in STB, or stock tank barrels, per acre foot. The model assumes that these 3 quantities are independent, each with a triangular distribution with the parameters shown. Note that each of these triangular distributions is skewed to the right. Then the key output is the recoverable amount in cell C15 in millions of STB. As is common in oil drilling models, this output is the product of the 3 uncertain inputs. To see how large a particular value in cell C15 is, a preliminary simulation is run, as I will now do with 5,000 iterations. The results show the extremes of the recoverable amount. For now, I will record the first and 99th percentiles of this distribution in cells E15 and F15. They show nearly how small and how large the recoverable amount can be. Then the relative size of the region, calculated in cell C16, is the percentage of the way the recoverable amount in C15 is from the minimum in cell E15 to the maximum in cell F15. Because the actual recoverable amount has a small chance of being outside these extremes, min and max functions are used in the formula for relative size to prevent it from being less than 0% or greater than 100%. Finally, the simulated capital expenditures and numbers of wells in rows 19 and 20 use the relative size in cell C16 to interpolate between the minimums and maximums in rows 4 to 7. And the total expenditure is calculated in column H. For example, if the relative size is 33%, then each quantity in rows 19 and 20 is 1/3 of the way from the relative minimums and maximums in rows 4 to 7. So far, only 3 individual cells have been designated as at-risk output cells. When time series are involved, it is useful to designate a whole series as an at-risk output. I will do this in rows 19 and 20. Note that each cell in either range is an at-risk output. For example, the risk output function in cell D19 indicates that this is the second output in the CapEx output series. Now I will run the simulation with 5,000 iterations. Here is the distribution of the recoverable amount. You might remember from the central limit theorem that sums tend to be normally distributed. An implication of this is that products tend to have a log normal distribution, and the recoverable amount is indeed a product. To check whether a log normal distribution fits this histogram well, I will run at-risk's distribution fitting tool directly from this histogram window. As you can see, the log normal distribution fits extremely well. For the relative size output, the histogram indicates bumps at 0% and 100%. These are due to the few iterations, approximately 2 out of 100, where the recoverable amount falls outside percentile limits in cells E15 and F15. These bumps appear in other histograms as well. For the yearly outputs in rows 19 and 20, you can look at histograms of each value individually. However, because each time series has been designated as an at-risk output, you can also look at a summary graph of the whole series. You can get this in two ways. First, you can click the Browse Results button, then the Summary Graph button, and then select the cells in the time series range. Alternatively, you can click the Summary button, then highlight the outputs in the time series range, and then click the Summary Graph button. In either case, the default settings are indicated in the legend. The yellow line indicates the means, the red band extends to 1 standard deviation on either side of the mean, and the green bands extend to the 5th and 95th percentiles. These default settings can be changed, but the defaults typically work well. If you would prefer a time series of box plots, you can now click the box plot button. This graph provides essentially the same information, just in a slightly different format.